In this video, we're looking at global maxima and minima. So remember, the highest and lowest values of a function over a given domain are known as the global maximum and global minimum values. Now, you can find maximums and minimums using stationary points, but some of these may be what we call local maximum and minimum. They're not necessarily the highest values or the lowest values. So we use the values of the domain to help identify the boundary coordinates of the function. And then along with the use of what we've done in previous videos of derivatives to identify stationary points, we're able to determine the global maxima and minimum values. So I'm going to show you by doing an example off the bat. So here we have our function and we have a domain listed here. We need to find the maximum value. So to begin with, we start like any other question when we're told to sketch it. We write out our function. And then we find our first derivative. All right, at this point we can start to find our stationary points. Now remember, these are our stationary points when the first derivative is 0. So we say 2x plus 1 equals 0, and we solve it like any regular equation. And we get x equals negative a half. So at negative a half, we know there's a stationary point. So at this point, we can go back and find our derivative to find the nature of these points. So remember our first derivative was 2x plus 1, so our second derivative is going to be 2. We don't have to do any further calculations here. And since our second derivative is greater than 0, we know we have a minimum. All right, so at this point now we can find our values for our domain. So we did have a domain of -2 and 2. We need to find what we call our boundary limits, the endpoints essentially of the function we're given. So what we do here is we just substitute these values into the original equation to find out what our y values are. So for the first one, we'll focus on y2. Now we just substitute these into the original equation. So we get 2 squared plus 2 minus 2, and that gets us 4. We then substitute in our next value, minus 2 equals minus 2 squared plus minus 2 take away 2, and that gets us 0. So at this stage we can list all the information we know, so let's list all our coordinates, because they can get lost in our working, and sometimes it's good just to write them out so we can see clearly what we've got. So we know we have a point here at negative a half and then 1/4. That's after we found the y value. This was what we call our minimum. Then we had our lower boundary or our lower endpoint, which was -2, 0. So lower endpoint. And then we had our upper endpoint at 2, 4. So we have 3 coordinates there. Now it's important to note that we can sketch this out. So let's do that. So if I just quickly sketch it, I know I've got a point over here at -2 and 2. Essentially there's some dotted lines going down here because these are our boundary points. Now obviously you're going to be using a ruler to make this more accurate. So our lower point was at -2, 0. We had an upper point over here at 2, 4. And then down here we had our turning point, which was negative a half and then -2 1/4. Alright, we knew that was a minimum, so it should look something like this. And we can just connect our dots. Now the question did say what's the maximum value. So looking at the sketch there, we can identify that 4, our 2, 4 point was our maximum. So we can say that our upper boundary or upper endpoint was our global maximum. And let's add the coordinates so we know. So we're going to look at another question now. So again, find the local and global maximum and minimum of this function in the domain. So again, we start the exact same way we did before. Start with your function. Find your first derivative. Find our second derivative while we're here. Alright, now we need to find our stationary points, and again, stationary points are when the first derivative equals 0. So now that we've got that, we can find these. So we know that 12x cubed plus 12x squared minus 24x equals 0. Notice there's a highest common factor there of 12. So we can divide everything by 12. So we get x cubed plus x squared minus 2x equals 0. We also have a highest common factor there of x's, so we can bring the x out the front. And we get x squared plus x minus 2 equals 0. That's a quadratic, so we can factorize that. Now again, you can use the quadratic formula if you wish, or any alternative method you prefer. So if we factorize that, we get this, and at this point we can list our values. So our first x is going to be 0 here. Our second x is going to be -2. Because remember, you're trying to focus on what makes each part 0. And this x over here will be 1. So we have 3 stationary points. And now we focus on one of them for each until we find what type of point it is. So to begin with, we're going to focus when x is 0. So we'll find what its y value is by substituting 0 back into the original equation. Put that in your calculator and you'll get an answer of -3. So our coordinates at 0, -3. We then need to determine its nature, and remember we use the second derivative for that. So I change all my x's in the second derivative to 0. And we get -24. Now remember, when you have a negative value, so our second derivative here is less than 0, we have a maximum. Now we focus on our second point. So we'll focus on x equals -2 now, and we'll find its y value. I'm not going to write everything out, I'm just going to put the answers in because we just did it previously. Our second derivative here since the second derivative is greater than 0, we have a minimum. And lastly, we do our last point. So when x equals 1, so we find its y value, which came out as -8. We put it into the second derivative. We get 72. So because our second derivative is greater than 0, we have another minimum. But now we need to check our endpoints for our domain. Now we've already done one. We've already done, because our domain was -2, 2. We've already finished our -2 value. We already found what that was. And up here, if you go to it, that was our minimum point here. So we don't need to do that again. It's just more work. But we do need to find its upper endpoint, so our 2 value. Now, if we just substitute that in to find the y value, we get 3 times 2 to the power of 4 plus 4 times 2 cubed minus 12 times 2 squared minus 3. Chuck that in the calculator and you get 29. So now, again, we always want to list our coordinates out so we know what's going on. So we'll list our coordinates. Because we've done so much working, it can get lost, so it's important to do this step. So we had a point at 0 here, and we said that was a maximum. We had another point at -2, -35, and that was a minimum. We had another point at 1, -8, and that was a minimum. And then finally, we had a point at 2, 29, and we said that was our upper end point. Now we've got multiple minimums and maximums going on here. We need to identify which is our local, which is our global. So I'm going to circle our maximums, or put a square around our maximums in blue. And I'm going to do a green for our minimums, because you only want to compare the minimums with the minimums and the maximums with the maximums. So if we're focusing on our maximums here, we want to find which one of these two has the greatest y value, or the highest. Now, since our upper endpoint has the highest, we know that this is going to be our global max, which means this here, up here, must be a local max. Because remember, local can be just any point. The global is the highest. So now we're going to focus on our green, our minimums, which has the smallest y value, and that happens to be this one. So this is our global min, and then we have a local min. Alright, so again, global maxes have the highest y value, global minimums have the lowest y value. So to recap the video, remember highest and lowest values, they are our global maximums and minimums. And we use the boundary coordinates we have to find our endpoints, along with all the derivatives, identify stationary points, determining what kind of stationary point it is, whether it's maximum, minimum, and then the last thing we do is decide which is our globals, which is our locals.